This video is on the heating curve of water for AP Chem. So last year in chemistry, you learned about the heating curve for water and the different calculations you can do to determine energy required to take water from different phases at different temperatures. So we know that water melts and freezes at 0 degrees Celsius. We know that it boils and condenses at 100 degrees Celsius. We know that as we put energy into our system, we will increase the temperature. It will go through a phase change. We'll increase the temperature again. It'll go through a phase change, and then we'll increase the temperature again. On this first one here, I'm below 0 degrees Celsius. This is my solid phase. Then along my line, I either melt or freeze. Then once I have changed everything over from a solid to a liquid here, then I'm going to increase in temperature of my liquid. Once I get to 100 degrees Celsius, my liquid starts to boil or evaporate, or it condenses. And then once everything has changed over to a gas, then I will heat again. So this is my gas phase. It's important to note that while I am changing in temperature, I am changing in kinetic energy. So along here, here, and here. When I'm not changing in kinetic energy, but energy is still being added, so along my phase changes, I'm changing in potential energy. So during my phase changes, that's my molecules spreading apart or getting closer together. And then during changes where I'm at the same state, that's molecules speeding up or slowing down. So kinetic energy is the energy of my movement, whereas potential energy is the spacing between my molecules. Some important numbers to note on here is we have our specific heat. I know that specific heat is the energy required to raise 1 gram of a substance by 1 degree Celsius. And it's also a function of how the substance absorbs energy. So if it's easy to change 1 gram of my substance by 1 degree Celsius, I'm going to have a very low specific heat because it's not going to require much energy to change the temperature. Whereas if I have a high specific heat, that tells me that it requires a lot of energy to change my temperature. So for water, when it's a solid, it has a specific heat of 2.1 joules per gram degree Celsius. As a liquid, 4.18 joules per gram degree Celsius. And as a gas, 2.0 joules per gram degree Celsius. The other number to note is my change, my heat required for fusion and for vaporization. So my heat of vaporization is the energy required to vaporize 1 mole of a substance at its boiling point. And then my heat of fusion is the energy required to melt 1 mole of substance at its melting point. So you notice these numbers are slightly different than ones we've talked about before. Here we have 6.02 kilojoules per mole, and for heat of vaporization, 40.7 kilojoules per mole. This is different. Before we used to have values of joules per gram, and now we have moles. So that's going to play a different factor in it, and that's going to manipulate kind of our calculation. So in our example, it asks us to calculate the energy released as 100 milliliters of water at 20 degrees Celsius in an ice cube tray is converted to 100 grams of ice at -5 degrees Celsius in our freezer. So I'm going to start by sketching my curve so I know which parts I'm using. So starting at 20 degrees Celsius, my water will will decrease in temperature till it gets to 0 degrees Celsius. At 0 degrees Celsius, my water will freeze to ice, and then from there it will cool to -5 degrees Celsius. So I have section 1, 2, and 3. So section 1, I am cooling the water, and here I use my formula. Delta H is mc delta T. So my mass is 100 grams. My specific heat, this is liquid water, is 4.18. joules per gram degree Celsius. And my change in temperature is going from 20 to 0, so it's 20 degrees Celsius. When I do that calculation, I get 8,360 joules. My second part of my heating and cooling curve is the freezing of water. I know this happens at 0 degrees Celsius, so I know that I can't have a change in temperature. So here, I can just use what I'm given, my 100 grams, and I know that my heat of fusion is 6.02 kilojoules per mole. So I can convert this into moles. I have, for water, 18 grams of water per 1 mole. And for my heat of fusion, I know that for every 1 mole, I have 6.02 kilojoules, and then this guy appears in joules, so I want to convert that. I know that for every 1 kilojoule, there's 1,000 joules. Multiply across the top and divide by the bottom, and I get 33,444 joules. Section 3, from 0 to -5, I am again cooling my ice. Here again, I use my delta H is equal to MC delta T. My mass is still 100 grams. Now my specific heat is of ice, so that's 2.1 joules per gram degree Celsius. And my change in temperature is going from 0 to -5, so it's a total change in temperature of 5 degrees Celsius. When I plug that in, I get 1,050 joules. And then my total energy is going to be my energy from 1 plus 2 plus 3. So when I add these all together, so this guy, and this guy, I get a total amount of heat energy of 40,850 joules. Looking back at the numbers given to me, 4 sig figs, 3 sig figs, 3 sig figs, 2 sig figs. I'm going to round this to 2 sig figs. So 43,000 joules or 43 kilojoules.